Ooh. All right. So yeah, I'm happy to have Cindy Rubio-González here with us from UC Davis. She's a graduate of our department. She did her PhD with Ben Liblet on bug finding, and she is now an associate professor at UC Davis, working on all sorts of cool stuff, but most importantly on numerical software and floating point, which is a topic that scares me. So it's a good Halloween talk. So go ahead.
Thank you for the introduction, Oz. So yes, I'm very happy to be here today to talk about some of the work that we have been doing on testing and analyzing numerical software. And let me, okay, so first of all, I would like to emphasize how numerical software is everywhere these days. So numerical software represents the foundation for a wide variety of software applications, including safety critical systems, such as control systems for vehicles, medical equipment, etc. And popular libraries, even for machine learning, computer graphics, computer vision, they all rely on numerical libraries, such as SciPy, NumPy, LAPACK, to perform numerical calculations. So these are just a few examples. Now, numerical software relies heavily on floating point arithmetic, which brings additional challenges for reliability and performance. Floating point, as you may know, is a widely used representation that approximates real numbers, and by nature, floating point introduces imprecision in numerical calculations. So these, along with the various precision choices that are available, make floating point programs particularly difficult to reason about. So my main focus is on numerical libraries and scientific applications, although some of the work I will describe today could be applied to other application domains. And in this context, scientific applications are often characterized for being large and complex applications whose results are difficult to interpret and for which performance is often critical. So today, I will first talk about our recent work on developing techniques for finding numerical bugs and diagnosing numerical inconsistencies. And in the second part of the talk, I will present some of our work on floating point precision tuning with the goal of improving program performance. So let's get started. So first, let me motivate some of this work. So we're going to be talking about numerical bugs. So what are numerical bugs? Numerical bugs are bugs related to either the final representation of real numbers or to mathematical aspects of the computation. So some questions that might arise is, how frequent are numerical bugs? What are the root causes, symptoms, fix strategies? So with the goal of answering these questions, we conducted the first large-scale study of numerical bugs in 5 popular libraries. So we manually examined over 800 bugs with the goal to provide a high-level characterization of these bugs to guide researchers in developing tools for finding and fixing these bugs. So 2 of the challenges that we encountered while conducting this study was, one, that these libraries were written in multiple languages using various version control and bug tracking systems throughout their lifetime. And also, most importantly, that there was a need for significant domain knowledge in order to inspect these bugs. So it was a time-consuming process and difficult. So I just want to give you some takeaways from this study. So we found that 269 out of 828 bugs that we inspected could be classified as numerical bugs. So this was 32% of all the bugs. And from these, we identified 4 general categories. So the first one is what we call correctness bugs. So these bugs are caused by any error in the implementation of an algorithm that have to do primarily with its mathematical or algorithmic structure. Then the second category was special value bugs. So these are due to the computation on special values such as sine zero, subnormal numbers, infinities, and nonce. Then we found convergence bugs. So these are bugs where an iterative or series approximation diverges or converges too slowly due to numerical errors. And finally, there were accuracy bugs. So these are bugs whose root cause is precision loss due to rounding or truncation. So that was like the main findings. Now, we also looked at these bugs from the point of view of what are the symptoms and whether it would be, how likely it is to automate the process of detecting them and fixing them. And here I just wanted to describe at a high level the findings. So we found that the majority of these numerical bugs, 77%, were revealed by producing wrong results. So all the bug categories suffer from this bug symptom. And this was followed by 13% experiencing a program crash, and the remaining 10% suffering from performance slowdown as a consequence of a bug.
So how do you quantify wrong results here? Sorry to interrupt. But...
Yes, so yes, that's a very good question. So we sample all these bugs by looking at bug reports. So in the bug report, basically that information was there, that the user was expecting a result when they got something very different. So that would be, yeah, that was like the main way to find out that was a cause. Does that answer the question?
Yeah, that's good. Yeah, thanks.
Okay, thank you. And yeah, so for all libraries except for the elemental, the top symptom was producing wrong results. And the second most common symptom was program crashes for NumPy, SciPy, and performance slowdown for elemental, LAPACK, and GSL. So we also classified bugs based on how likely it was to automate the detection or fixed. And so here I refer to as patterns, so bugs that could potentially be detected or fixed by applying a common pattern on the code. And analysis refers to bugs that could be potentially detected or fixed automatically after non-trivial analysis of the code, such as tracking the propagation of special values or estimating round-off errors. And then finally is domain-specific, which means that domain-specific knowledge is required to detect or fix the bugs, in our opinion. So in these cases, users detect the bugs by rerunning calculations to compare against less efficient implementations. And this is basically whenever they find that a result is suspicious, they'll go and look for a less, so a less performant implementation to just corroborate whether the result is correct or not. So kind of that hinted to differential testing, which is going to motivate one of the tools that I will describe in a few minutes. So in most cases also, it was interesting that in most cases, users seem to find the inputs that expose unexpected behavior almost by chance. And there was no indication of the use of tools or any other resources, either by developers or clients. So the paper has also some other lessons, but that would be like the findings in a nutshell. So does anyone have any other questions before I move on to talk about some of the tools we have developed to find some of these problems? Okay, great. So motivated by these findings, we have recently worked on 3 techniques for finding numerical bugs and isolating numerical inconsistencies. And the first one I will talk about today is called FPDiff. So FPDiff is an automated differential tester for numerical libraries. So in particular, FPDiff, because it's doing differential testing, is going to be able to find some of those problems that require significant domain knowledge in our study. So there, as probably I hinted at earlier, there are many numerical libraries implemented in different languages, offering different features. And testing numerical libraries is challenging for several reasons, including the inherent imprecision of floating point representations, as I mentioned earlier, and also the fact that there is not a standard in terms of reporting errors. So there is a lack of uniformity in dealing with inevitable errors. So as a consequence, it is not an exception that in this domain is very difficult to find oracles. So when oracles are lacking, a possible solution is to use, well, let me show you here an example. So let's say that here I pick one of the Bessel functions from JMath, and I just provide these two inputs, I get a result. So is this a correct answer or not? So often, you know, most of the clients of these libraries might not know what the expected answer is. So this is what I refer to as test oracles are often difficult to find. Now, when oracles are lacking, a possible solution is to use higher precision. However, simply using higher precision has several limitations, including that bugs inherent to the algorithm will not be revealed by simply increasing precision. So this is problematic because such correctness bugs constitute the largest portion of the bugs that we identified in our study. So we need an alternative to using higher precision to find these bugs. And our strategy, or another strategy would be to identify other implementations of the same function and evaluate them over the same input. So for example, here are functions that have similar functionality as the JMath function I had shown you. And if we provide the same input to all of them, we would expect similar outputs. So in this case, we get the output from JMath, and we also find that the output from all the other implementations is very different. So this could already hint at a problem with JMath. So this is what we know in software engineering, programming languages as differential testing. Now, the question is, how can we apply and automate the full process of differential testing in this setting of testing numerical libraries? So our solution is FPDiff. So this is an end-to-end tool for automated differential testing. And the input to FPDiff is the source code of the numerical libraries. So in our evaluation, we tested C, JavaScript, and Python libraries. And the output is a set of annotated numerical discrepancies. So the annotation is going to tell you how likely this discrepancy is a bug. Now, so FPDiff addresses 3 key challenges. And the first one is how to identify meaningful numerical discrepancies. So it is often the case that evaluating equivalent functions will result in 2 outputs that will not exactly match, but also they are not indicative of a buggy behavior. And furthermore, different libraries may produce different outputs when encountering the same invalid inputs. So this is problematic because this is all going to result in discrepancies, but they are not going to be discrepancies that, you know, correspond to bugs that need to be fixed. Now, the second challenge is in finding these equivalent functions in the first place. So determining which functions implement the same continuous analytical mathematical function is non-trivial because documentation can be unreliable and function names are often misleading. So we need to find a way to find these classes of equivalent functions automatically. And finally, we need to devise a way to automatically synthesize drivers for testing. And this can be difficult, in particular for libraries that are written in languages that do not provide type information. So now let me, I think my PowerPoint just crashed. Let me restart it. I'm sorry about that. Speaking of bugs.
Yeah.
Okay.
Now you have
I wonder if it's a numerical bug. I don't think it's a numerical bug. It could be.
It could be the slide itself. Okay, I'm so sorry about it. I'm going to. Okay, so I am here. Here. Yes, okay, sorry about that. Now, I wanted to mention that FPDiff is open source and it received a distinguished artifact award from ISTA. So if you are interested in trying it, we would be really happy to hear what you think about it. So let me go back to how this works. So I will only describe two of the challenges using an example. And the first is how to identify these functions that have equivalent similar functionality, which we call function synonyms. And the way we do it is that we evaluate these functions. So this is test-based. So we evaluate the functions over a series of elementary inputs to generate a characteristic vector. So here, elementary inputs are designed to result in well-defined behavior. And function synonyms that have characteristic vectors whose elements lie within a given error threshold are considered to belong to the same equivalence class. So for example, here on the slide, I have an example of 3 elementary inputs, and we get the results from testing all of these functions on each of them. And then based on the results in these characteristic vectors, we find 2 equivalence classes. One is highlighted in blue and the other one in yellow. So this is how we find these equivalence classes based on testing. And now, once we have identified equivalence classes, we need to test them to uncover the numerical discrepancies we are interested in. So we evaluate these functions over a series of adversarial inputs that come from test migration, inaccuracy-inducing inputs, and a special value inputs. And we also assign automatically a category from 1 to 6 that represents how likely this discrepancy is to be a bug, but I'm not going to be talking about that today. So, but the details are in the ISTA paper. And just to give you an example, so here we have an adversarial input that was a test migration input that we use from GSL. And here are the results. So this is basically the bug that I showed you in the earlier example. So this test migration input revealed the bug in JMAT. And this is due to an inaccuracy. So this is basically category 3 discrepancy that we assign based on our categories in I cannot see again the chat. Let me just put it very quickly in case there are any questions. Okay. So we use FPDiff to test special functions. And here I would like to just describe a couple of highlights of the evaluation. So the first one is that the function classifier turned out to be quite effective. So it discovered 126 equivalence classes encompassing almost 500 functions. And here, precision was affected by the choice of elementary inputs. So our elementary inputs lie within a domain. And in this case, in the cases that we failed to map correctly was because, that was not like the correct domain input to use. And in terms of recall, the recall was mostly affected by the effectiveness of the driver generator, because this process is test-based. So if we are not able to generate a driver in the first place, we will not be able to classify the functions. And in terms of the differential tester, it uncovers 655 discrepancies. And these were automatically reduced to 327 that we call likely bugging. And we manually inspected all of them, and we reduced this to 125 distinct reportable bugs. And 30 of them have been fixed, 9 happen to be known bugs for which there were already issues posted, and 25 have been acknowledged but not fixed yet. And I just wanted to say that beyond those 227, like outside of those 327, those are cases where we have the lowest category, basically. That means that there were discrepancies that that were mainly due to error handling. So basically, libraries output different things on errors, and those are not really bugs, but I think that those are also very interesting to look at, in further studies. So finally, I would like to show you 2 examples of bugs found by FPDiff. So here is an example of a bug revealed by an inaccuracy inducing input. And this is a discrepancy in the equivalence class of the polygamma function representing 2 bugs. So one is an inaccuracy, and then the other is an unexplained complex return. And in this case, this has a non-obvious fix, and the developers are still trying to figure out how to fix this problem. And I have a second example. So this is an example of a discrepancy exposed by a special value input. And this is in the equivalence class of the factorial function. And this is a case where a double is generated from an AND. So this is a problem in SciPy. So this is a case of an obvious fix with a non-trivial implementation. So in this case, the fix is quite simple. So check for special values and do something. But it turns out that the implementation didn't lead to an easy fix in the code. So the pull request contain the pull request to fix this bug contained, a commits, 26 changes, and the discussion among developers went on for over a month. So there is a link to this PR from the paper. And this is all I have about FPDiff. So if anyone has any questions, I think this would be a good stop point.
I was just wondering how you pick the elementary inputs, and what does elementary mean?
Yes, so and in the paper what we chose was the input domain. I have to double check 0 to 3. 0 to 3, and this was picked based on the classes of functions that we are testing, because this was focusing on special functions. And elementary, what we want to say with that is that these are inputs that are likely to trigger well-defined behavior. So it's well-tested inputs that yes, but yeah.
Cool. Thanks.
Okay, good. So let me briefly talk about another recent tool we have worked on. So this is the FPGen tool. So this is a tool for generating floating point inputs that maximize error. And let me just give you some background on why this is needed. So when testing numerical applications, well-known metrics such as code coverage are no longer sufficient. So we need a way to find inputs that expose corner cases in computation. So just imagine the case in which, maybe you have a 0 and you will have good coverage, but it's not really going to expose an interesting case in terms of the computation. So an example of these inputs are basically values that expose large floating point errors in the program's result. So finding large error-inducing inputs is not trivial, and previous work has shown that only a very small portion of the input domain can cause large errors. And so I guess this is also the basis for FPDiff with elementary inputs, that we are making this assumption that most inputs or inputs in certain domains are likely to not cause errors, and we are leveraging that for classifying functions. So in this case, it's kind of, now what we're leveraging is also the problem, right? Now we want to find those inputs that cause error, but those are very few in the input domain. Now, the state of the art uses various heuristics to search through the input space, but they are limited in efficiently exploring large search space or in the number of inputs that they can handle. So the goal of FPGen is to generate multidimensional floating point inputs, such as arrays and matrices, that maximize error. And the insight here is to identify the very few error-inducing inputs by exploring the operations where precision loss and cancellation may occur. So let me give you here a high-level description of FPGen. So FPGen has 3 modules. And in the first one is going to inject inaccuracy checks in the program. So what this means is that for each floating point operation in the program, we are going to insert these checks that are checking for precision loss and cancellation. And here what we're trying to do is that we said before that code coverage is not going to expose these problems, but now by explicitly checking for these conditions, we are going to effectively add branches to the code that when we test, we're going to try to cover. And the second component has two parts, so it's concretization and symbolic execution. So the concretization component iteratively partitions the input variables into two groups, and one group is initialized with random values and the second group is going to be symbolized. So the high level goal of this is to scale symbolic execution, because if we have all the inputs as symbolic execution is not going to be able to be as effective. So this partitioning allows to scale the approach, and this is also basically trying to minimize the impact that all the new branches that we are adding, add. Now, so FPGen is going to check the status of the symbolic execution engine, and if the engine times out, then FPGen is going to reduce the number of symbolic executions, so it's going to keep iterating. So this partitioning of variables into concrete and symbolic keeps changing until time is out. So now symbolic execution has as goal to maximize code coverage. And because we added all these special branches in the code that we believe expose interesting cases for the computation, then it's likely that symbolic execution is going to generate inputs that cover these branches, which are likely to lead to high errors. So from all these inputs, we measure the error that they expose and pick those that are error-inducing inputs. So that's the high-level idea of FPGen. Now, FPGen was evaluated on a collection of programs that take as input arrays, vectors, and matrices. And we consider three baselines. So the first one is just doing random input generation. The second one is comparing against the state-of-the-art tool S3FP. And the third is just using symbolic execution, which is we use the engine ClearFloat, but this is without transforming the program, just to see how effective is symbolic execution at triggering these high errors without anything else, just on the original program. And here are the results. So in the x-axis are the benchmarks, and the y-axis indicate the maximum error in log scale that each tool triggered for each benchmark. And the higher a number in the graph, the better. So FPGen triggered the highest error across the 4 input generators in the majority of the programs, except for 3 cases in which either no errors or similar errors were triggered by all the tools, and 3 cases in which S3FP triggered a larger error. So we suspect that in these cases, FPGen failed to trigger a cancellation. And as a summary also, out of the 21 programs, the random generator and S3FP triggered an error in 13 programs. ClearFloat could not trigger any errors in any of the programs. So this is the symbolic execution engine working on the original program. And FPGen triggered an error on 20 programs. And in terms of the magnitude of the errors, FPGen triggered an error that was on average, more than 2 orders of magnitude larger on average. Yeah. So any questions about FPGen? So that's basically like all the description I have for it. I'm trying to check the well, I'm not checking the chat, I'm just checking the actually like the hands in the participant list. So let me know if at some point someone has a question. And finally, I would like to talk about pLiner. So pLiner is a tool that automatically isolates code that triggers compiler-induced numerical inconsistencies. And let me tell you a little bit about the problem that motivated this tool. So usually floating point is underdefined in the language specification. And as a result, compilers have a great degree of freedom in generating floating point code. So this freedom comes at the price of producing possibly different numerical results when using different compilers, or even when using different optimization levels with the same compiler. So we refer to such numerical inconsistencies as compiler-induced. And one such inconsistency was recently observed in Lagos. So Lagos is a hydrodynamics application developed at Livermore. And here, what the developers at Livermore found was that when porting Lagos to a new architecture, they observed a compiler-inducing consistency when using the Excel compiler with the compiler optimization level 03. So as shown in the table, Excel 03 produces a very different result compared to Clang, GCC, and even Excel with 02. And you could use the Excel flag QStrict, which disables basically the optimizations. And that gets rid of the inconsistency, but at the same time, the developers are not able to take advantage of the performance improvements. So the developers were really interested in finding out what was the cause of this. And they spent weeks doing that, and they were able to isolate the function, but they couldn't go beyond that because the function was very large and complex. So motivated by these kind of problems, we developed pLiner, which helps to find such the root cause of such inconsistencies. And pLiner takes as input the program and the inputs, and it's going to perform a hierarchical code isolation that identifies suspicious code areas. And then it increases precision, so precision enhancement transforms the program, transforms the floating point operations in those code areas. And here the assumption is that if we increase precision, those inconsistencies are more likely to go away because the optimizations are going to affect less the program. So that's assumption. And here, once we have this program that is using higher precision in those code areas, we test them and we compare them against, a specific compiler or a code that is not optimized to see whether the inconsistency disappears. So if the consistency disappears, that's good news. So what the algorithm does is try to zoom in that code area to try to minimize it. And if the inconsistency persists, then the algorithm will try to explore other code areas. So as the final result, pLiner will report the minimal code area so that when transformed to higher precision, the inconsistency disappears. So yeah. And just a few more things about the precision enhancement. So this is source-to-source transformation. And I already said here that the assumption is that, we're using higher precision in the hope of emulating real arithmetic and assuming that transform code to higher precision will yield better results. And we apply this precision transformation at the function level, which means that the whole function is transformed to higher precision, and also at the region level. So you could transform only a loop or a specific basic blocks or expressions in a specific lines. And just to illustrate the hierarchical code isolation, so the idea is very simple. So we start by doing transformations at the function level, and let's say here that we are able to isolate two functions, 2 and 5, and that means that when you increase precision in those two functions, the inconsistency goes away. So then we sum in, If the program has loops, we start searching within the loops because those are known to accumulate more error. But if not, we still search over the function. At some point, we lower to search on basic blocks and then lines. And in this case, the algorithm would have isolated lines 1, 2, and 3 from function 2 and line 2 from function 5. Okay. So we evaluated pLiner on the Lagos case that I described earlier to see whether it was effective at isolating a line, and also on 100 synthetic programs that suffer from compiler-induced numerical inconsistencies. And finally, we also trigger numerical inconsistencies on the NAS parallel benchmarks. So we compared against Herobrine. So Herobrine is the state-of-the-art tool for identifying the origin of floating point errors. So Herobrine instruments the binary code to perform each operation in both the original and higher precision to calculate local errors, and then it tracks them down to identify their origin. So, and we compare against it. So for the Lagos case, pLiner successfully isolated one line, which was line 130. And when enhancing the precision of the operations in this line to 120-bit precision, the numerical inconsistency disappears. So this information allowed the developers to still reap the benefits of the optimizations applied by XL03 while obtaining consistent results. And we manually inspected the binary of this function, and we found that the division operation on line 130 is transformed to reciprocal plus multiplication when applying the O3 optimization, and this was introducing floating point exceptions. So that was the root cause of this inconsistency. Now, in terms of the variety programs that suffer from compiler-induced numerical inconsistencies, we generated.
I didn't understand. Did you automatically find that line? I got confused about that.
Yes. We automatically found the line. Yes.
Okay.
Yeah.
And so perhaps I missed something, but what was the point to that line?
What was the point? That if you increase precision, then the inconsistency triggered by the compiler goes away.
I see. So this was the first line where that happened in the code?
No, so it was the only line that when you increase precision for this line, when this operation is computed in higher precision, then the optimizations that are being applied do not trigger floating point exceptions.
But what if you have multiple lines?
Oh, yes. So pLiner can also find multiple lines. Yes.
Okay, so you have to guess the two different ones, or?
Yeah. So the search will partition the program and try basically increasing precision in different areas of the code to try to see whether it makes a difference for reproducing the inconsistency or not. Yeah.
Why can't you just, I mean, this would be expensive, but increase the precision everywhere and just find the first point where the outputs diverge?
That could be another way to look at. I am not sure how it compares in terms of experiments, but it's a bit, yeah, it makes sense. Yeah, and what we did is that we increased the precision in the whole function to isolate the functions in the first place, but then we started doing the search within the function. Yeah. Great. Thank you for the
Hao had his hand raised up, but I think he lowered his hand. So I assume he doesn't have bed.
Question as Laurie, on, yeah.
Okay.
Thank you. And yes, so for the synthetic programs, we generated 100 programs, 50 for the Power 8 platform and 50 for x86. And pLiner was able to isolate the inconsistencies in 87 out of the 100 programs. And in 85% of the cases, we were able to isolate one single line. And this took, I mean, these are synthetic programs, so, you know, smaller, so the runtime was very, very low. And in terms of Herobrine, so Herobrine doesn't provide support for Power 8, so we couldn't perform a comparison for those 50 programs, but for the x86, Herobrine was able to isolate the inconsistency for three of the programs. And finally, so for the NAS programs, so first we tested all these programs to see if they suffer from these numerical inconsistencies due to the compiler, and we could not find any. So then our second attempt was to focus on the NAS programs that include a verification routine. So in this verification routine, there is an error threshold that is used to assess whether the result is correct or not. So then we did a search over the values of this error threshold to see if for certain value we could trigger a numerical inconsistency when compiled with O3. And we found 3 cases. So one was for the CG program and 2 for the SP program. So these are the 3 cases listed here. And then what we did was to test pLiner to see whether it was able to isolate anything in these functions that could hint at, you know, what was the cause of this inconsistency. And for one of these programs, we were able to isolate a function, so it was a full function. And for the other 2, so one, it was a case like the one Loris mentioned. So it was a case where it was several lines. So it was 4 lines. And in the third case, it was just a single line. And this took less than 40 minutes. So yeah, these programs are a little bit larger. Yeah. So any questions? So this is all I have for the tools for bug finding and diagnosing numerical inconsistencies. If anyone has any questions, I'm happy to take them.
I have a high-level question.
Yes.
So, I mean, you presented, you know, a number of tools for finding bugs in existing code, but like,
yes.
what did you learn in terms of language design or better practices for writing numerical code? Like, what would you do if you were tasked with, you know, designing the next generation, whatever? Like,
yeah, that's a really good question.
Only use
what? Sorry.
Only use booleans.
Yes. So let's see. I would say so testing obviously is very important. So when we were doing the testing of numerical libraries, it was very surprising that there was very little overlapping among tests. You know, for similar functions. So there is a need for you know, putting more effort in testing, definitely that. The second one would be, let's see. Error handling is a big issue, and I don't know exactly how to address that because as I said before, there is like no standard on how one should handle errors. So some libraries were resorting to throwing exceptions, other libraries were just returning, you know, special values or like zeros, or so that is very problematic because if you are now moving from one library to the other, you might get just different results from error handling. In terms of more of like the design, let me think. Yeah, I think those would be like the main points. Yeah, I don't know if, yeah, I think those would be.
Cool.
Yeah, and there is just a lot of diversity because these are like different languages like Python versus C, C++. I mean, also there is a big difference in documentation. So I would say like a best practice would be obviously to document these. Very difficult to parse. Like some libraries do have information about like the types or you know, corner cases, but the information is actually encoded in how the text is formatted, as opposed to having explicit text, or even worse, there is just no documentation. So there is very little documentation on what are invalid inputs and what's the expected behavior on that. So then I would say that another area of improvement could be, well, testing and documenting the functions, and then the third is like maybe having like a standard on how to handle errors across all these libraries.
Yeah. And another question regarding, like you showed this line where if you increase precision, things work out. But you can imagine cases where, you'll have, I don't know, like 1,000 lines where, each of them contributes a little bit of error, and then fault localization doesn't work anymore. So do you encounter such cases in practice, or am I just imagining?
I can see those cases. So when testing these tools, I didn't encounter, well, I guess one potential case of that would be the function where we could just isolate a function.
Mm-hmm.
So yeah, that would be one of those cases in which we couldn't really point out one specific expression or like a line.
Mm-hmm.
So it was the whole function. So yes, it does happen, and it's very problematic because I mean, some of the things that we're thinking, like some of the feedback that we would get from people external to these applications is like, well, just disable the optimization and move on, right? Like it's giving you like you just disable it. But in most scenarios, performance is just so critical that they just need to find out like what and how to fix it to keep going and at least have a consistent result. So yeah, even at the function level, I think that this is very useful still because, as you saw, like just debugging this could take a lot of time.
Yeah.
Yep. Thank you. So.
Well, I have a question
yes,
about
please.
FPGen. So could you please go back to the slides showing FPGen? So
yeah, let me.
Yeah.
That one.
Yeah. So at some point you mentioned that you insert some branch using inaccurate check injector. So I was wondering what's exactly usage of this branch.
Yeah. So the idea is that if so we're checking whether the result of this operation so one thing that I didn't say is that when we are comparing also against a program in higher precision, so there is always a reference. So then in this check we are just checking like whether there is like a big precision loss or a likely cancellation in there. And if that condition is true, then that branch is going to be executed just because the condition was true. And the idea with symbolic execution is that we hope that symbolic execution engine will generate an input that will try to exercise this new branch that we added. And if that branch is exercised, then an input for which that condition is true will be generated and likely to lead to higher.
So I was wondering how, because for each numerical operation you have to maybe add a branch. So how many branches are there, and how do they impact the scalability of symbolic execution?
Yes, that's a very good question. So it's going to be 3 branches per point. So the paper describes these in more detail. And also we are very careful so that the checks, we are not introducing like additional checks in the condition. So it's just like 3 checks. But still, we are increasing the number of paths. And obviously that's a problem with the scalability of symbolic execution because we know that the technique suffers from path explosion. So the way to counter that was to do this concretization symbolization, like dividing the inputs into 2 groups, and that seemed to work in order to still have it to scale. But yes, I mean, we're exacerbating the problem of path explosion by adding this, but in the end, it turned out to be okay in practice with these other optimizations in concretizing some of the inputs.
Thank you.
Thank you. Yes. Yeah. So, any other questions? Very good questions. Okay. So let me see. So we have like 7 minutes left. So maybe I'll just introduce the problem of precision tuning, and yeah. So, but I'm not going to go over the tools in detail. So just to give you an idea of what this problem is about. So this is kind of the opposite of what we are doing, the contrary to what we are doing with the bug finding tools, where we increase precision. So here is the problem that we have encountered is that in most cases, programmers do not have the expertise to reason about how much precision is needed in the programs, and many times they overestimate. So they use more precision than needed. And the main downside to it is that if you are using, let's say, long double or even something higher, or double versus float, you are going to see the repercussion on the program performance. So the tools that are looking at automated precision tuning are focusing on the problem of, if you tell me how accurate you need your program to be, I'm going to try to reduce precision in the program with the goal of still giving you an answer that is accurate with respect to whatever constraint you have, but also while improving performance. And let me just give you an example. So this is just a small code fragment, like a C program that calculates implements the Simpsons rule. And here, most details are unimportant. So I just want to point out that there are two functions, fun and Simpsons, and all the floating point variables here are declared in long double, which is an 80-bit representation. And there are two calls to math functions here on lines 2 and 3. And here the question is, okay, so if I'm willing to tolerate some error in the result computed by this program, can I reduce precision anywhere here to improve performance? And the answer is yes. So here is an example of such a program. So at a high level, the programs look identical, but there are some important differences, in particular in how the variables are declared, the types that are used for their declarations. So here for variables having lowered from long double to double, and another 4 having lowered to float. And also one of the function calls has been replaced to call an alternative implementation of the sign function, which is in single precision. And now, if I run this tune program, it turns out that this program is 78% faster than the program on the left, while computing a result that lies within the error threshold provided by the user, which was 10 to the minus 8. So we have been working on this area for a while now. And yeah, so I'm not going to have time to talk a lot about,
Is the precision, is it on one input or on all inputs?
So you can provide multiple inputs. So that's the scenario. So let me just show you here, like for one of the tools, PRECIMONIOUS, which is, one of the first tools, now quite old. So basically, this is a dynamic approach. So you will need to provide several inputs. And here, this is just going to apply a systematic search over the types of variables and function implementations and give you a type configuration that uses less precision while giving you a speed up. And this is going to be only with respect to the inputs tested. So there are no other guarantees otherwise. So the hope is that this is going to be used as an assistant. So I always like to highlight that. So, if you are the domain expert who wrote the application, hopefully this type configuration will guide you on where to explore. And you will not just go and blindly apply the configuration, although you could also do that. But yes, the limitation is that this does not provide a guarantee beyond the inputs that we'll consider during the tuning process.
There is this work by Eva Darulova, for example, that can produce certification bounds. Would you be able to check using those that actually
Yes, so she does have a recent paper where she is combining dynamic precision tuning with estimating errors. Mm-hmm. And that's a very promising work. So one of the, in my opinion, one of the main blocks right now to have the estimation of errors is mainly on the structure of the program, right? Like limitations in loops and, you know, branches and things like that. But being able to guarantee, even if it's not a whole program, right? Like a code fragment, that would also still be very useful. And this is one of the very first tools, so it's like 7 years now old, but recent work has been moving in that direction. Yeah, thank you for bringing that. And so before I conclude, I just wanted to tell you very briefly about another couple of things I have been doing. So one is about bug swarm. I don't know if any of you have heard about this work. I have been working on this for the past 4 years. So this is a data set of reproducible failures and fixes. So we have a completely automated infrastructure to create this data set. And we have over 3,000 of these samples, bugs and fixes. And the idea is to use them in the evaluation of tools for bug finding or automated program repair. So we are actively working on bug swarm. Everything is open source. So if any of you is looking into applying a large scale evaluation of a tool, or you are interested in empirical studies, please reach out. And we're very interested in providing support for you to try bug swarm. And the other area is on bug finding for error handling problems. So we have been, most recently, we have been combining static analysis and machine learning for bug finding in Linux code, which is something I started doing in Madison, and also, other large C applications. So this is another topic I'm very interested in. And with that, let me just thank my collaborators. So most of the work, like all the work I described today was led by my students here at UC Davis. So acknowledge, thank you to them. So here are some of my current collaborators and former collaborators, in particular for PRECIMONIOUS. And thank you some of our sponsors. And with that, I would be happy to take any remaining questions if you have any. I know that we're 1 minute over.
Okay, thank you, Cindy. That was great.
Thank you. Yeah, we had lots of questions throughout, so yeah. But just in case, or if anyone has any questions later on, please feel free to reach out.
I think I also need to run in a couple of minutes, but I just want to say there is one of my students, Yuhao, is in this talk, and the one that asked several questions, and he has a paper this year at FSC that you might find interesting. So if you have some time and you can stay around a little bit and talk to him.
Yeah.
Yeah, that would be great. Yes. Yeah. We can stay here on the line.
Okay. Otherwise, if there are no questions, I'm going to leave, and you can stay in.
Okay. Thank you so much again for having me, and I hope to see you in person soon.
Yeah, hopefully soon.
Yeah.
All right. Thanks a lot, Cindy.
Take care. Bye.